So here we have another differential equation example, and here we're given the following equation. We're asked to solve this x squared y plus 1 dx, y squared x minus 1 dy. And this is a first order, first degree equation that we are going to use the separation of variables approach. And we recall that when we have an equation of this that's in the form of this form here, we have some function of x times a function of y dx plus a function of x and a function of y of dy. This usually lends itself well to the separation of variables technique. So usually by inspection we can find an integrating factor, which is usually in the form of 1 over one of the functions in x times one of the functions in y. And the purpose of this is to reduce that original equation into a form like this one, where you can see the first term is all in x and the second term is all in y. So let's look at this this equation and see if we can figure out how to do that. So for this equation, we can define or assign as follows. The function of x for our integrating factor would be x minus 1, and the function in y would be y plus 1, such that we would now have an integrating factor of 1 over x minus 1 times y plus 1. We can use this integrating factor then to reduce our original equation to this form. So now you see we have successfully separated the variables. The first term is all in x and the second term is all in y. So now we want to work to solve this integral. So for the first term, we can just perform some algebraic long division, and we can come up with a new expression for the first term that still equals the same, but it's just expressed differently. It's in a form that's easier to integrate. Likewise, we can do the same with the second term, simply just doing algebraic long division. And again, you see we come up with an equal expression for that doesn't have the function or the variable with the power of 2 in it. So we can now utilize this to help us perform the integration. So starting with the equation we had before where the variables are separated, we can use the results of the division that we just did to rewrite these equations in this form. And of course this form lends itself much easier to integration. So now we can just take each term and integrate directly. So doing that, this term here, we would just perform the integration of each term and do it in terms of the variable defined there. So the first term is x, second term is y. And we are going to just, for clarity and completeness, integrate the 0 in terms of those variables, because we know that will result or could result in some arbitrary constant that we could evaluate if we were given initial conditions. So performing this integration, which we can do directly, we should get 1/2 x squared plus x plus natural log of x minus 1 plus 1/2 y squared minus y plus natural log of y plus 1 equal to some constant. We can now clean this up just a bit. I mean, that is technically the answer, but we can get it in a little more compact form by multiplying through by a factor of 2, and we can rearrange some of the terms and utilize some of the properties of natural logs. So doing that, taking the original equation, we can combine it in this form, and this is what we're calling the general solution to the differential equation given above.